Hello everyone, and thank you for joining us for this webinar. The webinar today will cover modeling, simulation, analysis, and operation of power plant controllers or PPCs, particularly for renewable applications. In this webinar, we will present how ETAP PPC solution leverages an electrical digital twin from design to validation and automation of renewable power plants. We will then give you a glimpse on how we extend ePPC with dedicated HMIs and ETAP eSCADA for asset health monitoring, predictive analysis, and preventive maintenance regimes to optimize plant production. So let's go ahead and get started. ETAP utilizes a model-driven electrical digital twin with automated analysis, predictive calculations, network optimization, validation processes, and an intelligent, secure power plant controller hardware to ensure local grid code or standards compliance are maintained throughout the power system design and operations lifecycle. The need to perform simulation studies of generating power plants is increasing nowadays. Whether it's a new interconnection request or an existing facility, electrical grid codes require documents or plant models that substantiate the compliance to the minimum technical requirements in order to permit the connection request or permit the facility to continue operating. ETAP transient stability, time domain load flow, harmonics, and additional modules allow users to conduct power system studies considering the logic of the power plant controller, which we will cover in more detail in this webinar. These studies provide a greater understanding of the plant behavior under incidents that are internal or external to the system or due to set point changes in the outgoing active power, reactive power, or power factor, and any other disturbances. Mirroring the controller logic between design and operation phases together with intelligent and secure power plant controller hardware ensures reduced commissioning time, compliance with local grid code and standards, as well as a smooth generation plant operation. In this webinar, we will use PV power stations as an example of a renewable power plant. Other types of renewable power plants can include wind, hydro, solar thermal, and more. The principles explained using PV power plants can be applied to other types of renewable power plants as well. We will focus, however, on large-scale PV systems designed for the supply of merchant power into the electricity grid. These types of systems are differentiated from most building-mounted and other decentralized solar power applications because they supply power at the utility level rather than to local users or groups of users. The generic expression utility-scale solar is sometimes used to describe this type of project. There has been a lot of debate over the threshold. However, we will consider all systems above 4 megawatt AC as utility scale power. In contrast, the world's largest solar park as of March 2020 is spread over a total area of 10,000 acres or 40 square kilometers and has a total capacity of 2,245 megawatts. A renewable power plant is a huge investment that requires control, routine maintenance, and continuous insight to keep it running efficiently, safely, and profitably. In a typical solar plant, hundreds of thousands of PV panels, up to millions, are usually hardwired to inverters that convert AC to DC power. They include transformers, switchgears, electrical balance of plant systems, large lithium-ion battery energy storage systems or ESS, and/or reactive power compensation devices. Now, by their very nature, PV cells produce a DC voltage. This DC voltage is not compatible with the grid, and that's basically where the inverters become an integral part of the solar power plant. Therefore, the fundamental role of an inverter is to convert the DC power derived from sunlight into AC power compatible with the grid. Modern day power plant controllers are designed to collect feedback from the grid from the point of connection or point of coupling and adjust the plant output to provide voltage and frequency support. This quality-controlled AC power output is collected and combined from many inverters. Like any other utility-scale system, the output is stepped up and distributed through a substation. A PV plant requires many inverters to process the output of multiple arrays. Each inverter is capable of individual control functions, but must coordinate as a unified regiment to appear as a single source at the point of interconnection. The variable nature of renewable energy introduces power quality concerns, including frequency and voltage control, that may negatively impact the reliable performance of a power system. Therefore, in today's dynamic energy generation environment, power plant owners require sophisticated and integrated control solutions to meet a variety of operational compliance and interconnection standards. So let's take a look at some of these challenges in a little bit more detail. Let's take an example of our general setup through an ETAP one-line diagram. This is the one-line diagram that we'll be using throughout the presentation. So let's go ahead and get familiar with our setup. The one-line diagram includes a grid connection, a point of interconnection, a point of measurement for our utility grade meter, our step-up transformers, in this case a 3-winding transformer, and of course our collector system or the collection system that includes multiple feeders providing solar power into the network. As we double click and we look inside this composite network, we can see a setup of photovoltaic arrays that are connected through various protected devices and cables and their individual step-up transformers and are interconnected into the collection system. An important step in assessing project feasibility and attracting financing is to calculate the electrical energy expected from the PV power plant. The energy yield prediction provides the basis for calculating project revenue. The aim is to predict the average annual energy output for the lifetime of the proposed power plant, which is typically 25 to 30 years. The typical procedure for predicting the energy yield of a PV plant is through time step simulation software that runs typically at hourly or sub-hourly steps. And that may include estimated losses, site conditions, and historical irradiance. These are good for estimation, but where they fail is to include detailed AC and DC losses, auxiliary power or balance of plant, grid availability, grid compliance losses, as well as the power plant controller performance. Developers who are using non-model driven tools are usually not aware of or do not consider several additional losses and therefore are not calculating a long-term yield prediction over the lifetime of the project with a higher uncertainty analysis. Typically, an investor will look for a higher level of confidence in the energy yield prediction, typically expressed as the P90 value, or the annual energy yield prediction that will be exceeded with 90% probability. This is only possible by utilizing a model-driven power system analysis solution. To illustrate this, let's switch back to our one-line diagram where we can see that we have included all the impedances of the electrical system, including the cabling, the transformers, and so on and so forth, as well as the ability to include time series data for various photovoltaic panels. And this time series data can include data from the profile library, including temperature adjustment, as well as considering the physical characteristics of the PV panel. For certain panels, you can also include time series data in terms of an Excel file that may be defined using historical or estimated irradiance levels at that particular site. You can also include the controller as part of the power system model, which we'll go through in a little bit more detail, but the plant controller can be defined such that it's associated with a set of inverters, a set of meters, a set of PV panels, including other controllers, as well as energy storage devices. Once the single line diagram, the controller, and the impedances have been defined along with the time series data, ETAP can simply give you a time series calculation at the press of a button. Once the calculation is finished, you can easily navigate through the time slider and see the real reactive power, voltages, and any other variable that you would like to see utilizing the display options. You can also see the same information in terms of a plot. So we can go ahead and plot one of our transmission lines here, including active and reactive power, and visualize the information that we have seen as in terms of time series data. This data is essentially a function of time and includes active and reactive power for our tie line. You can easily double click to isolate a particular trace, and you can zoom into a particular area in the system and identify the values in more detail. Should you like to track the data, you can also track the information along the curve and also track multiple sets of data at the same time. Utility scale users require a configurable controller. This is because the goal is to maximize power output and therefore revenue while supporting a stable and reliable grid using this configurable capability. However, the logic used for power plant controller must be capable of precision tuning and control not only during design but also the operations phases. So let's understand this a little bit more detail. It is possible that assumptions during the design stage may lead to a slow or fast responding controller that may need to be adjusted or tuned during the commissioning phase. Having access to the model, the controller logic, and other capabilities allows for updating the simulation models and increasing the confidence level such that it can be guaranteed that a similar performance will be achieved in the field. The logic used for the plant controllers during design stage must be the same as that for the operations phase for yet another reason. You run the risk of meeting grid code requirements during the design stage, but not during operations if you utilize a controller logic in simulation mode that is not commercially available to be used in operations. The cost to design, rewrite, and maintain two controller logics can delay commissioning and increase startup costs. A power plant owner or operator can easily lose their license to operate or incur financial losses should their plant fail to meet ongoing or evolving operational grid code requirements. Therefore, there's a need to continuously monitor the power exchanges, power quality, and grid conditions, as well as proactively adjust plant performance should it not be within grid code requirements. Finally, a single point of management is needed for remote monitoring of plant performance. A monitoring system is an essential part of a PV plant. Monitoring devices are crucial for the calculation of financial damages and confirmation that the EPC contractor has fulfilled its obligations. Automatic data acquisition and monitoring technology is also essential during the operational phase in order to maintain a high level of performance, reducing downtime, and ensuring rapid fault detection. An ideal monitoring system allows the yield of the plant to be monitored and compared with theoretical calculations and raise warnings daily if there is a performance shortfall. Faults can therefore be detected and rectified before they have an appreciable effect on production. Without a reliable monitoring system, it can take many months for a poorly performing plant to be identified, and this can lead to unnecessary revenue losses. Therefore, the ultimate aim of the designer is to create a plant that maximizes financial returns by minimizing the levelized cost of electricity. Levelized cost of electricity is the present value of the price of the produced electrical energy, which is usually expressed in units of currency per kilowatt hour. Considering the economic life of the plant and the costs incurred in the construction, operation and maintenance, and of course the fuel costs. Levelized cost of electricity does not take into account the site environmental factors other than those considered in the historical data, such as panel soiling, that may be accelerated due to unforeseen conditions, technical faults such as inoperative inverter or shattered PV panel due to dust or rocks, as well as changing site conditions such as vegetation. A power plant controller therefore must be able to detect and adapt to these changing conditions. The key is therefore to use a digital control twin of the actual power plant controller and the power system model together with time series analysis and forecasting to guarantee its performance under various grid and plant operating conditions. Therefore, an integrated solution with a situationally intelligent power plant controller is the key to maximizing yields and meeting TSO or transmission system operator stability and power quality requirements at the point of interconnection. ETAP model-driven power plant controller solution includes a digital twin of the electrical system combined with advanced automation hardware and system protection that can optimize and control complex electrical systems. ETAP PPC integrates with on-site solar PV, energy storage, wind turbines, and more to manage grid compliance and cost-effective generation in real time. ETAP PPC solution includes a dynamic system monitoring recorder, eTesla, which is a hardware and software solution that performs the assessment and continuous audit of actual operation versus expected response. The system operating condition is compared with the established grid code rules for compliance reporting and evaluation. Continuous monitoring of steady state and dynamic plant response is also used to tune the dynamic models, identify controller parameters, and confirm power plant controller response under actual operating conditions. A developer of a power plant usually performs a number of steps shown in red. The basic steps remain the same, that include design and analysis, pre-commissioning, monitoring, control, post-commissioning, and management. Therefore, from the feasibility stages to the dynamic model design, compliance studies in steady state and dynamic, over to SCADA integration and tuning and validation of the controller, HMI design, and finally the control and parameterization of the controller is typically done as part of the development of the power plant. However, an EPC goes through all these additional stages that include the engineering, construction, and operation of the power plant. And therefore, an integrated, unified solution is required that can take the power system model through all these stages and provide all the necessary functionality at these critical or crucial steps. ETAP power plant controller solution reduces risk in the planning phase by utilizing the power plant controller models during the power system simulation studies. Grid conformity therefore becomes predictable and guarantees a smoother interconnection approval using the built-in or user customizable dynamic models. The solution also includes the ability to perform studies that ensure compliance with multiple grid codes and standards. The grid codes standard models can be used for the power plant controller using a rulebook that increases the transparency and investment security all the way from planning to operations. Grid codes are technical specifications which define the parameters a facility connected to a grid must meet to ensure safe, secure, and economic functioning of the electrical system. The facility can be a power generation plant, a solar farm, or any other grid-connected source. Both ETAP power plant controller as well as the dynamic system monitoring recorder have access to the grid code rulebooks that include voltage and frequency regulation right through, real and reactive power capability and control, islanded operation, emergency operation, and more. Now, we mentioned earlier that an optimal PV plant appears to the grid as a single unified source of power while maximizing active power output and providing grid support. This is accomplished by balancing two modes of operation: active power control and automatic voltage regulation. Coordination between generator owners and system planners is crucial to a balanced grid. It is important to regulate the allowable amount of power at the point of interconnection. Active power control limits generation at the point of interconnection to predetermined set points. This purposeful limitation is called curtailment. Grid support through automatic voltage regulation is done by regulating reactive power. The figure shows a simplified control logic for plant control. The source of the plant level set point, such as the P and Q set point, may be one of the authorized users sending a manual command. Changes in the set point from the user are passed through a PNID control and through a velocity limiter. The PNID controller constantly compares the current set point with the actual value as it appears on the grid. This is referred to as a closed loop feedback. And this is what is tricky and difficult to achieve in simulation mode. Discrepancies between the current set point and the instantaneous output at the point of interconnection manifest as an error which is used to correct the output. If the change in the set point is too extreme, the output will overshoot the set point before it has time to correct itself. To prevent operator-induced overshoot or transients from the set point, the velocity limiter transitions to the new set point gradually. Each inverter is equipped with a controller that provides localized closed-loop control based on its commanded set points. The local inverter's controller is constantly communicating with the plant controller. If an inverter stops communicating with the plant controller, it would appear offline or unavailable and omitted from the plant control scheme. An inverter may still run and produce power even if it's unable to communicate with the controller. This emphasizes the importance of a closed-loop control scheme. The closed-loop feedback at the point of interconnection detects the unknown contribution and scales back the commanded output to compensate. Unlike traditional generators, the prime mover or fuel source is often uncontrollable. With PV generation, weather and sunlight conditions cannot be controlled. Irradiance may be too low or irregular for the plant to meet the demand. Similarly, partial cloud cover can affect different areas of the plant disproportionately, causing the output to fluctuate. The closed-loop nature of the PNID loop allows the plant controller to provide partial compensation by increasing the requested set point to all inverters. Inverters which are affected by cloud cover will only be able to produce the power available from their limited irradiance, but other inverters can produce more than their fair share to compensate. In ETAP, the controller can be modeled in a couple of different methods. You can essentially model the controller at the TSO level. You can model a power plant controller, and you can also model a controller at the individual component level, for example, as shown for this battery energy storage. Each controller is linked together in order to coordinate the control within the electrical system. So let's take a look at one of our controllers in a little bit more detail. If you open up our solar plant controller, the very first thing that you would define are the associated devices, as we discussed earlier. This associated devices list includes additional controllers that this controller can communicate with. So in this case, the solar plant controller is communicating with our energy storage controller as well as a TSO. Further, you can also define whether it is actually monitoring or controlling or commanding another controller. In this case, we want our solar plant controller, which is the secondary controller, to actually control the energy storage device. However, we want the power plant controller to only monitor the TSO. In other words, the transmission system will command the solar plant controller as the secondary controller, and then the solar plant controller will dispatch whatever set points are required for real and reactive power to the energy storage devices, STATCOMs, as well as other PV inverters in the system. Therefore, it is crucial to have monitored and controlled set up appropriately. Further, you can define the controller information in terms of UDM, or you can essentially utilize a dynamic link library or DLL as a means to define the controller logic. The controller logic includes a number of parameters, which we can see all of them either in a single flat list, or you can essentially see them through a grouped manner. Since we were discussing real and reactive power control, we can see various modes of operation for real and reactive power control, along with their initial set points and dispatch values. The reliability services, therefore, fall into two categories: frequency support and voltage support. Frequency support is primarily focused on controlling active power and maintaining the fine balance between supply and demand across the bulk electrical system. Voltage support services are concerned with the control of reactive power and maintaining stable system voltages required to transmit power through the grid. In most cases for PV sites, both active power control and automatic voltage regulation act independently from each other. The main exception is when the facility is operating at its maximum MVA capacity, where the two of them are linked. So let's talk a little bit about frequency support. Throughout the day, the load on the bulk electrical system will vary. System operators need to balance supply and demand in real time to maintain reliability, adjusting demand from resources throughout the day. The key indicator for measuring the supply-load balance is line frequency. In North America, the electrical system obviously operates at 60 Hz. When demand rises, there is not enough supply to meet it, line frequency goes down. This is commonly referred to as a frequency droop. The tolerances for frequency variation is very small and it's closely regulated. Let's talk a little bit about voltage support. The system voltage is critical for reliable power transmission. Therefore, a steady fixed line voltage is critical for the function of most electronic equipment. For these reasons, system operators and generators play an important role in regulating and supporting voltage. Line voltage is primarily supported through using reactive power. Throughout the day, line voltage can differ depending on the system state and loading. It's not an uncommon requirement for a plant to be capacitive during some points of the day and inductive during other periods. This dynamic reactive power control is a function that PV inverters can excel at. To accommodate the different needs of system operators and planners, a typical PV plant offers 3 different modes of reactive power control. Each mode regulates reactive power control through different parameters. So let's take a look at the first control in more detail, which is voltage control. The voltage control is the most commonly used mode at grid-tied PV sites. Throughout the day, system voltage can fluctuate with the loading effects of the system. A PV plant must be able to provide voltage support in both directions by being able to both absorb and export reactive power. To boost transmission voltage, voltage control mode injects reactive power into its output, boosting its overall apparent power. When system voltage is above nominal, the plant will begin absorbing reactive power to pull the voltage closer to nominal. Unlike other control modes, voltage control will only influence the system voltage and might not always hold at the specified set point, depending upon the strength of the system being connected to. This voltage control is implemented as a droop with a deadband. The droop characteristics are typically provided by the regulator or owner. A typical droop is 4% with 1% or less for the deadband. The amount of reactive power support is calculated using feedback from the line voltage at the point of regulation. This scheme allows operators can easily predict a plant reactive power response at a known voltage level. So let's take a look at a couple of scenarios with using ETAP software for voltage control. So let's take a look at our voltage control mode through the power plant controller. You can find it inside the Q control, where mode number 1 essentially is power factor and mode number 2 is voltage control. And we can see that this particular function is disabled. And the nice thing about the program is you can simply enable or disable this control and change your scenario or your what if analysis. You can also adjust the ramp rate functions, including the ramp rate limiters, the reactive power reference, voltage reference, and the power factor reference as needed. We've already run our base case without the voltage control operational, so we can see the voltage fluctuations at the POM bus or the point of metering bus. Since this is a balanced system, we'll just focus on phase A voltage and see the fluctuation on this bus. So here we can see our fluctuations on the POM bus as a function of time. So let's go ahead and see, once we enable our voltage control function from our controller, what happens to our POM bus voltage. So we'll simply open up our scenario for voltage control and run. So our calculation is now completed, and we can go ahead and close our scenario and look at our plot once again for the POM bus. Here we can essentially see that the controller has stabilized to a voltage control reference value close to 100% fairly quickly, and we can see what the ramp rate or the velocity limiter was set to in terms of this controller, and we can see that it's able to maintain the voltage close to 100% throughout the entire simulation period. So once again, you can compare with the before voltage control scenario and after voltage control scenario and see that this power plant controller is essentially effectively maintaining the voltage at the desired set point. Now that we've looked at an example for voltage control, let's have a quick discussion and a demonstration of active power control. So active power control is one of the two system directives. The primary objective of active power control obviously is to control the real power production at the point of interconnection. Therefore, the balancing authorities or the off-takers and the power purchase agreement will basically decide how much power a plant is required to produce at any given point in time. The plant is obligated to track that set point and produce the commanded power when possible. The natural variability of irradiance and demand on the grid presents controllers with unique challenges. A good controller attempts to adapt to disturbances in the environment and the grid to meet the set point. Accurate and dynamic control of production is achieved using a closed feedback loop control. And this, of course, must be simulated in practice as well. A meter at the point of interconnection basically tracks the plant's contribution as it's seen on the grid. Of course, if there's more irradiance potential than needed to maintain the set point, the inverters must be commanded to limit themselves. Purposeful limitation of the production, once again, is what we refer to as curtailment. So in our next scenario, we'll essentially produce or provide two different TSO commands. This is where the TSO is commanding the power plant controller to adjust its real and reactive power set points in a combination. So therefore, in our initial setup, the TSO will be commanding the power plant controller to 15 megawatts, and it will maintain a real power of approximately 55 megawatt, which we will see per phase as about 18.5. At 120 seconds or at about 2 minutes, the TSO will command the voltage to 101%. So this is a voltage command, not a reactive power command, and command the real power to 20 megawatts. At 5 minutes or 300 seconds, the TSO will command reactive power to 9 megawatts and real power to 30 megawatts. And then finally, at 9 minutes or at 540 seconds, a power factor command will be given at 91% and the real power will be adjusted to 20 megawatts. So this is a very typical realistic scenario in a compressed time frame to illustrate the fact that the TSO can send multiple commands in multiple formats to the controller, and it's able to adapt and adjust to any combination of commands given to it. So let's see this in terms of the ETAP software. So we can open up our TSO controller, which is providing the commands to the solar plant controller. Go ahead and look at our schedule command, and we have 3 different time frames as we discussed earlier. So the first time frame we are dispatching at 120 seconds, followed by a dispatch at 300 seconds, and finally a dispatch at 540 seconds. And this essentially includes our 91% dispatch with our reactive power and active power command as we saw in our timeline. So let's go ahead and run this simulation. So we'll go ahead and bring up our scenario for TSO command and go ahead and press run. Once the calculation is completed, we can go ahead and bring up our plot. And in this case, we're going to bring up the plot for our point of interconnection. and see the results for real and reactive power both. So as soon as the plot is available, we can turn on our trackers for both real and reactive power, and we can see that at the initial point the real power is 18.5 megawatt times 3, which is 55 megawatt, and our reactive power is approximately 3.2 again times 3, which is about 9 megawatts or so. And then we have an initial dispatch, if you recall, of 15 megawatts. So we are essentially operating at about 5 times 3, 15 MVARs, which is the red line, and the real power stays at about 55 megawatts. Approximately at 120 seconds, or about 2 minutes time frame, which we can see on the x-axis, we dispatch the controller to go to 101% voltage. So that essentially drops the reactive power down to a lower number, and we commanded the real power also lower to approximately 20 megawatt. So that accelerates down to about 6.5 megawatts here, times 3 again, which is approximately 20 megawatts or so. And we essentially stay at that value till we get to about 300 seconds or 5 minutes. And at that point, we are essentially dispatching the reactive power again to 9 megawatts. So the reactive power drops to, in this case, about 3. You can see the fluctuations as it's trying to adapt along with the irradiance adjustments that are happening in the system. And it's able to stabilize at about 3 megawatts per phase, or 9 megawatts. And the real power is commanded to 30 megawatts. So that's 10 megawatt per phase. And we can see that the real power is essentially tracking after some initial small transient in the system at about 10 megawatts or so. And then finally at 540 seconds, which is at about 9 minutes or so into the simulation, we can see that the real power was again commanded to 20 megawatts, so it drops down to approximately 6.67, and the reactive power was adjusted to 91% power factor. Now that may have to be computed or looked at separately in a plot, but that we can see very easily on the one-line diagram as well. So if we go ahead and close this plot, go back to our single line diagram, take our slider all the way to the end of the simulation time and look at the amps or MVA along with the power factor, we can see that we are actually at 91% power factor at the end. And we essentially started with 98% power factor. So we can see that the last command that takes it to 91% has been met as well. Now, in our previous example, we looked at active power control based on a TSO command. We've also looked at voltage control by itself. Now, what if the TSO is commanding voltage such that the voltage is unable to be met by the power plant? So this is a scenario where we are commanding 100% voltage, and at the same timelines, 2 minutes, 5 minutes, and 9 minutes, we're commanding 101%, 102, and 105%. So normally when the VAR support is demanded from the plant, each individual inverter will respond with a proportional change in its reactive power or Q output. Every inverter is basically capable of varying the amount of reactive power it provides based on its capability curve, which is also defined as part of the inverter control. If the reactive power required is too high, which may be a bit too high here in this case, which is about 105%, then it can burden the inverters, causing them to curtail the active power in order to maintain a fixed or a constant MVA. So by introducing a capacitor bank, a reactor bank, a static VAR compensator, or even a StatCom, you can essentially offload some of the burden onto these devices. So let's take an example of a TSO commanded voltage control where we are varying the voltage from 101 to 102 to 105% with our inverters in the system and our StatCom that is not sized appropriately, and see whether we can deliver the voltage that has been commanded by the TSO. So we'll go ahead and bring up our scenario, run a case where we don't have sufficient reactive power capability in the system, and see what happens to our network. So once our simulation is completed, once again, we can go to our plots, and in this case, we can see at the point of measurement in terms of voltage, what is the situation in terms of the TSO sending the commands to the power plant controller. Do we have enough reactive power capability, and can it deliver the set points that we asked it to deliver? So if you recall, originally our set point, once again, was 100%. So that's essentially, we can see at our initial condition. And at about 2 minutes or so, we sent a command to increase the set point to about 101%, which it's able to meet. And then approximately 5 minutes, we sent another command to increase the rate to 102%. So we can see the ramp up to 102% at about 5 minutes or so. And approximately at 9 minutes, we sent a ramp once again to 105%. So we can see the step up and the time it takes to get to 105%, but we can see it never achieved 105%. We are now limited to 104.3%, and we are unable to deliver the commanded voltage value. Now this could be because, of course, we don't have enough reactive power capability or other factors. This is, of course, for the engineering team to decide, and one of the possible solutions here is to increase the size of the reactive power compensation devices and size them appropriately to deliver the maximum amount of voltage that the TSO may ever command in that system. So let's take an example of that, where we change the size of our STATCOM in this case and see the effect that it has on this facility. So this is where our STATCOM is defined in the system, and its current rating is about 22 megawatts. And again, for the sake of simulation, we can switch to another revision that I've already configured the STATCOM to a slightly higher size. And then we'll go ahead and run our simulation once again. That includes essentially our case where the STATCOM has an appropriate size to deliver the power needed. So our simulation is now completed. We can go ahead and now open up the POM bus voltage once again, and now compare the voltages with a STATCOM size of 22 megawatts versus a STATCOM size of 30 megawatts. And we can see that our previous result, as far as voltage was concerned, we were clipped at 104% or so. And with a new size, we are easily able to achieve 105%. So of course there's fine tuning and precision required in adjusting the STATCOM size, but this is of course one of the strategies that can be used to make sure that you can meet the commanded voltage set point within a certain ramp rate and a certain reference value without any difficulty. Now that we've looked at voltage control, let's talk a little bit about renewable smoothing, which is a hot topic in terms of energy storage and variability of renewable power, including wind and solar. So integration, of course, of renewable energy resources to a power system cause power fluctuations because of the intermittent nature. Of course, this is because the grid has very little storage capacity, and the balance between electricity supply and demand must be maintained at all times to avoid a blackout or any other cascading problems. Intermittent renewables are challenging because they disrupt the conventional methods for planning the daily operation of the electric grid. Their power fluctuates over multiple time horizons, forcing the grid operator to adjust its day ahead, hour ahead, and real-time operating procedures. So again, if you take an example of solar panels, solar energy is inherently only available during daylight hours, so the grid operator must adjust the day-ahead plan to include generators that can quickly adjust their power output to compensate for the rise and fall in solar generation. This is of course predictable because we have sunrise and sunset at predetermined times. In addition to daily fluctuations caused by sunrise and sunset, the output from solar panels can also change suddenly due to clouds. Variability caused by clouds can make it more difficult for the grid operator to predict how much additional electricity generation will be required during the next hour of the day. So it becomes difficult to calculate exactly what output of each generator should be in order to accomplish the load following phase. Fast fluctuations in output from wind or solar not only disrupt the hourly load following phase of grid planning, but also the second-to-second balance between electricity supply and demand. Today, the grid operator sends a signal to power plants approximately every 4 seconds to ensure the total amount of power injected into the grid consistently equals the total power that is drawn or demanded. Because wind and solar increase the magnitude of sudden power generation shortfalls or excesses, the grid operator requires more reserve power ready to respond at a moment's notice to ensure the grid remains balanced. So therefore, one way to reduce these effects is to smooth out the power production using energy storage systems. The use of energy storage technology has the potential to be far faster than regulation by gas or steam turbines. This fast response time can minimize momentary electricity interruptions, which are more costly than sustained interruptions. These storage technologies can vary output rapidly, changing from no output to full output within seconds. Now, besides smoothing in big solar plants and wind farms, the grid operator asks energy providers to provide power with minimum difference from one time to another. We add this constraint on top of the smoothing problem. Then we determine a minimum possible size of energy storage system so that the smooth output power is maintained during the day ahead forecast period. So in other words, when we look at the PV profile or the variability, which is shown in this gray line, we use the energy storage system to essentially smoothen out these disturbances or fluctuations and convert it into something smoother as represented in this blue line. So let's take a look at renewable smoothing in terms of simulation using ETAP software. If you go ahead and look at our solar power plant controller here, this power plant controller also has a function for renewable smoothing, and the logic that it's utilizing is the ETAP rate limiter logic for smoothing. You can of course replace this with your own logic, but the ETAP rate limiter logic includes multiple methods of doing renewable smoothing, including moving average filter, where you can define the filter length, and it also features an advanced Gaussian filter that allows for multi-objective renewable smoothing, so that you can not only do the renewable smoothing second by second, but you can also do adjustments in the commanded output together with the renewable smoothing, which makes it more complex. But the Gaussian filter gives us that capability to do so. And the ETAP rate limiter is where you would define the drift that you are allowing the power plant to have. In this case, it's 8 megawatt per minute. That means you are allowing the plant to drift plus or minus 8 megawatts per minute and not provide very tight control through the energy storage device. So let's take an example of the simulation with a very loose or drifting power plant and see what kind of fluctuations we have in our system, and then come back and tighten this rate limit and see the difference that the energy storage device makes. So we'll go ahead and run our simulation for renewable smoothing, and once our calculation is completed, we can go ahead and look at our tie line once again in terms of real and reactive power and see what kind of impact our energy storage device is making in the system. So here we can see that the active and reactive power is fluctuating drastically. We can of course disable our reactive power for a temporary purpose and see that our active power is fluctuating significantly in the system, and there's not much control that the energy storage device is providing, because we are allowing the plant to drift up to 8 megawatts per minute, which is a significant drift in the system. So let's go ahead and tighten that to about half megawatt per minute and see the effect that the battery storage has on this system. So here we're going to go ahead and change this to about 0.5 megawatt per minute and essentially rerun our simulation again. So once our simulation is completed, we can go ahead and bring up our tie line cable again and go ahead and plot our real and reactive power, and let's see whether the energy storage device was able to smoothen out our fluctuations. So here again, once we disable the reactive power temporarily, we can see that the energy storage device is essentially trying to fill in the gaps, but we can see a lot of fluctuations that need tuning in terms of this controller. So once again, you can see the effect if you allow the system to drift from, in this case, 16.5 to 14.5 megawatts. And here you can see the tightening between 15 and 16 megawatts, what is essentially being provided in the system. Of course, you can go through a couple of iterations and find the appropriate energy storage size and the appropriate tightening of the controller to ensure that you smoothen out these fluctuations and achieve a tighter band in terms of real power adjustment. If we go back to our simulation where we set up our renewable smoothing at 8 megawatt per minute and we rerun our time domain simulation, we can then take the information from our battery plots, our renewable plot, as well as the total system power, and use Python to essentially give us a chart that combines all that information together. So here I can see my renewable power, my battery power in red, and the total power. So we can see that as the battery is discharging and charging, we can see the effect that it has on the total power in the system. And we can see whether we are able to provide smoother power or not based on this 8 megawatt per minute ramp rate relaxation. And let's go ahead and rerun this case and combine all three together. So therefore, with 2 megawatt per minute, this is the output combined together for once again the renewable power, battery, and the total power. And we can see that as the renewable power drops, the battery essentially comes in and fills in the gap, so you can see the total power increasing. And when you follow this orange line, you can see a smoothness that's provided in terms of the total power in the system. And of course, these fluctuations can be adjusted by adjusting the velocity limiter on the battery and the energy storage device, and of course the PV controller, and provide additional smoothing. But you can essentially see the envelope is fairly smooth as compared to the blue line. Another common case that is analyzed during design as well as to be understood during operations is whether the power plant can deliver the appropriate P and Q requirement at the point of interconnection. This is different case than the command case where the TSO is commanding the power plant controller to a particular value. This is essentially to test the entire range of P and Q capability and the ability of the PV plant or the wind plant to deliver the real and reactive power at the point of connection based on the capability of the power plant. So we can go ahead and essentially look at our controller and define the frequency support curves, and we can also define the PV capability curve. And we use these curves to then adjust the power plant controller to track and follow this curve and give us a result whether this power plant, along with its reactive power compensation and energy storage devices, is able to deliver the P and Q required to satisfy the grid code requirements at the point of interconnection. So let's go ahead and run our simulation for our current case based on a certain size and see our results. So our simulation is completed, and again, in the interest of time, we've gone ahead and used Python to put together our generated power, which is the power being generated from the PV plant based on its current size and capability, shown in this blue line. We have also included the theoretical reactive power that's possible from this plant based on the capability of various inverters. And we've also included an orange line, which is a reference line from the power grid, which is the PQ capability, or in this case, the real reactive power capability required at the point of interconnection. So we can see that the theoretical line is essentially less than the blue line, which is the generated reactive power, but it's definitely much less than the reference value or the required reactive power demanded from the system. So therefore, in this case, we can see that there's insufficient reactive power available in this system. And one of the ways to increase that, again, is to essentially increase the size of our STATCOM. So if we go ahead and increase the size of the STATCOM, and once again, in the interest of time, we've already done that. And once you increase the size of the STATCOM and rerun the simulation, you can see that the generated reactive power, which is again the blue line, is now close to the reference line or the required reactive power from the system. And you can see that that's accomplished by essentially increasing the size of the available reactive power in the system, or essentially upsizing the STATCOM. So using this comparison chart, you can fine-tune the size of the STATCOM such that it is not overly expensive and meets the reactive power requirement of the system. So now that we've looked at the electrical one-line diagram and the controller logic working together hand in hand in a closed-loop environment, providing functions such as active power control and reactive power control, we can then take that entire logic, including the parameterization of the velocity limiters, the rate limiters, and of course the PNID control system, and take that entire programmable controller logic and deploy it into the ETAP power plant controller hardware. By essentially a press of a button, you can simply deploy this logic into the controller using the deploy button inside the program. The hardware interface can be visualized, mapped, deployed, and of course updated. This update essentially implies the ability to hot swap the logic, which essentially means you can simply go to your settings for the controller, adjust various parameters or the parameterization, and once you're satisfied with the simulation, you can simply go back to the associated devices and deploy this logic into the controller. This essentially reduces the downtime by allowing this hot swap of logic and the parameters. The power plant controller therefore includes the various functions such as active power constraint, ramp rate limiting, reactive power control, voltage control, and a SCADA interface to flexibly expand and adapt to functions of any plant topology and provide reliable grid integration. And this of course has been now validated and tested through our simulation model in a closed loop environment. Therefore, that same logic is now available in this hardware for real-time data communication. So this is a typical system architecture for a solar monitoring system that ETAP provides, that includes ETAP ICE, power plant controller, and the dynamic system monitoring recorder, all working together across multiple sites. You can set up these devices on a single site, such as a single PV plant, or a combination of PV plants, or a combination of a mixture of wind and PV plants. You are of course not limited to renewable power. This can be also applied to gas turbine as well as conventional power plants. The idea being the ETAP ICE RTU and the gateway are essentially monitoring various devices in the system, including the inverters, energy storage inverters, STATCOM inverters, and other converters in the system. They are also monitoring the transformers, switch gears, relays, and other IEDs using a combination of Modbus, IEC 61850, DNP3, and other protocols. The ETAP ICE RTU then communicates with the power plant controller, which provides the secondary control to the entire system. And that communication is typically done over DNP3. And the power plant controller is essentially sending the input and output commands over to the monitoring system so the operator can visualize and through HMIs understand what is the response of the power plant controller, and when needed override the power plant controller through manual commands as needed. The power plant controller from site 1, site 2 all the way up to site N can essentially be fed into a single dashboard or individual dashboards for each site. And of course, these dashboards are then available on mobile for you to also visualize and see the trends and get an overall summary of each individual site in the system. ETAP SCADA, along with the HMIs, provide the awareness and business intelligence required to get the performance of the entire system portfolio through mobile as well as desktop environments. This includes key performance indicators along with alarming and notification, and investor overview, or essentially a yield production dashboard, along with user configurable reports. You can also configure the dashboard to include performance ratios, as well as maintenance applications such as workforce management and maintenance management. And these can also be supplemented with schematics of the one-line diagram, so you can visualize and understand the status of various components in the electrical system. So therefore, when we look at the parameterization for the power plant controller and we see all of these values such as P control, Q control, renewable smoothing, and so on, when we deploy this logic, it essentially is available inside our web HMI as well as SCADA system, so that certain individuals who have authorization and access can also change the parameterization when the system is online. So let's take a look at that particular page once we deploy this controller into our system. We can see from our HMI for our solar SCADA that the power plant controller operating limits, including the parameters, labels, values, and of course the units, are available in terms of parameterization that the user can essentially modify and adjust as needed. These again are adjustable through authorized individuals, and they require an appropriate access level in order to adjust versus just purely being visualized for display purposes only. So here we can see a quick HMI of our electrical system that we've been looking at in the past. So we can see our point of connection, including our tie line, the 4 feeders, as well as the STATCOM and the energy storage device. So this information is available on our SCADA HMI, along with the real-time measurements, as well as the ability to control the system, such as breaker open and close, and so on and so forth. However, the first step is to essentially look at the parameterization. So from our plant controller settings, the parameters, the labels, the values, and units are essentially available for the controller to adjust. If the operator does not have the appropriate access levels, they're able to view the information. However, with appropriate access levels, you can go ahead and actually adjust or parameterize the power plant controller while still online, if those adjustments are minor and they have been previously validated through the power system model. So now that we've looked at our parameterization, let's take a look at our main dashboard. The main dashboard can include various panels that you can rearrange in any combination. So in this case, we want to have our metering and weather together. You can also even adjust the panel style and the color settings the way you would choose to do so. You can also add a new gadget or edit this particular layout. So here we are essentially looking at our metering at the plant level, along with our interconnection data, as well as our SCADA server status and the overall status of all our inverters in the system, along with the site conditions and any electrical data that may be relevant to the overall system. In the electrical overview, as we saw earlier, we can essentially visualize the single line diagram that the operator can essentially adjust and control. What's important here is this single line diagram is actually exported from ETAP. So therefore, if you go to the program and you update the simulation, reparameterize the power plant controller, validate that inside ETAP, you can export the single line diagram into the HMI without having to rebuild it. So that essentially saves a tremendous amount of time in updating and fine-tuning the one line diagram and the system, especially during the commissioning stages. You can also look at the individual plant inverters one by one, including their AC and DC power and other status such as the fan condition, the operating temperature, and you can individually adjust the MPPT tracking and the set point for each inverter and get alarming on every single inverter in the system. And that inverter in this case can be a battery inverter or the actual PV array inverter. You can also get the energy production report on a daily, weekly, monthly, or yearly basis. So in this case, we can see that this battery inverter is actually controlled by the PPC and we don't have any manual control over it. You can also see the aggregated inverters at the feeder level. So we are essentially looking at feeder A from our example. And that includes PV array A 1 through 21. And you can also see the feeder transformers at an aggregated level. So these are essentially the step-up transformers of the PV array inverters that are going into the collection system. So that includes the transformer temperature, tap position, as well as the alarming and the relays that are alarming this particular transformer. The power plant controller itself is giving you a visualization of what the power plant controller is actually doing, along with the control that it's actually set to. You can also change the power plant controller to manual mode and send individual set points directly from the HMI. And you can also visualize what the power plant controller is doing in terms of its point of interconnection monitoring and any alarming that is being generated based on the power plant controller logic. You can also take this data and visualize it on a geospatial view, including the vehicle or crew tracking in terms of maintenance support, visualize any alarms that are occurring in the system, look at various events that may be happening in the network, including any alarm generation or any audit information that you want to track. Of course, we've looked at our parameter settings that the user can adjust when they're changing the parameterization on the system. And you can also look at various trends such as the solar array power, current, irradiance, any converter power values that are relevant, and of course the total system power that you may be interested in. So now that we've looked at the power plant control, let's take a few minutes to talk about grid code monitoring and assessment. So the obligation of any renewable plant is to comply with the grid performance requirements. And in order to do that, you also have to monitor steady state and dynamic plant response. The consequence of non-compliance could be payment reduction, disconnection, and of course any kind of conflict in the system. So that's where the dynamic system monitoring recorder comes into the picture, that provides online assessment of grid code compliance. And it can do online and continuous operational audits based on operation versus expected response of the system. This includes detailed event reports for compliance traceability, and you can use this for power plant controller analysis and tuning. So therefore you can compare the simulated response of the power plant controller with respect to the operations of that power plant controller. And this dynamic system monitoring recorder sits inside the substation along with the power plant controller, and it provides the information to the ETAP SCADA HMI as usual. So the basic principle being that you can take the data acquisition from the system, the grid code rules from ETAP, combine it with the operational twin that has the electrical system model as well as the real-time data, do the compliance assessment, and report the compliance in real time. So you can get a daily, weekly, monthly, or yearly compliance audit reports on a continuous basis. So therefore, for this purpose, we use this dynamic system monitoring recorder that essentially acts as a digital fault recorder, a dynamic swing recorder, sequence of event recorder, power quality recorder, a long-term recorder, continuous disturbance recorder, as well as has PMU or real-time phasor monitoring capability. So the benefits, of course, are to do power quality monitoring that can be used to verify the power quality of supply and reduce energy costs and production disturbances. And you can use it to identify flicker and other disturbances in the system. The same recorder is also used for wide area measurement to improve grid reliability and early detection of faults in the network. You can of course use it for power plant monitoring that includes detailed grid response and plant characteristics, and of course for tuning the plant control, including compliance with the NERC MOD requirements for dynamic model tuning. You can also use it for additional capabilities such as voltage stability monitoring, power oscillation detection, as well as subsynchronous oscillation monitoring. And it also is a multi-function fault recorder, so therefore you can also use it for the analysis of protected device operation and combine it with the ETAP AFAS or automated fault analysis system to determine the fault location and identify the type of fault in the network. So in summary, the ETAP PPC is a model-driven control and renewable plant management system that offers user-friendly control logic designer. It has ETAP in the loop situational intelligence for providing closed loop control, simulation, and validation of the control in a closed loop environment. It connects with ETAP SCADA for real-time autonomous operation, and you can use the direct connection between ETAP and the power plant controller to hot swap a validated logic at any point in time. Thank you once again for attending this webinar on ETAP Power Plant Controller, and we look forward to your questions, feedback, and comments. Thank you.